And we're going to start in math practice. The easiest way. Start there. All right. So a couple things. I want to do today again. We're in so analyze part 2 out of 3, and this is the theme here is just how do we get data to talk to us instead of just laying on the page. How do we make it scream what to do next? How to make improvements? It's going to tell us how to make improvements. And the best way to do that is with doing hypothesis testing. So just a quick review of last week. Remember this one here? Pretty simple one. Average temperature since 1950 was 87.5. Last July was 94. Is that temperature statistically significantly different than the average? And the steps were, and again, you're going to hear this about 10 times today. Define the objective and the confidence level. In this case, we did 95%. We want to be 95% confident, which is the same as an alpha of 5%. 95% confidence level, alpha is 5%. So if it's it's 90% confident, then alpha is going to be 10% or 0.1. Decide if it's going to be a 1 or a 2-tail test, and that's usually by this hypothesis test. Formulate a null and an alternative hypothesis, where the null is the status quo and innocent until proven guilty, and then the alternate hypothesis is not the null. And the only objective of hypothesis testing is to try and figure out if we can reject the null hypothesis. That's all. We're going to select a test distribution and a critical value. So for every type of data set, there's this type of distribution. We want to know, is our data normal, bell-shaped curve? In other words, everything's kind of nice and stable. Doesn't have a lot of outliers and tails and everything, so you have a bell shape where the center of the bell is the mean, and you have some data on either side of it, kind of like my weight, like this one, remember? Like that one. And then we calculate our test statistic from a formula. So in this case, this is what we did here. And then we compare that number, and that becomes our test statistic, and we have to set up the goalposts, and we get those from a table. And in this case, because it was a 2-tailed test, all we want to know was the temperature different, right? Not hotter or colder. And from the table, we realized 1.96 was our goalpost. And in this case, our test statistic came out at 1.857. So it was inside the bell, not in the rejection region. So we could not reject the null hypothesis. So that's a quick review of that. Again, many of the hypothesis tests, they all operate the same way pretty much. And I think you remember this table from our PowerPoint. These are a bunch of different types of hypothesis tests that we're going to kind of go through. These are all the tests that are used for continuous data. Continuous data is data that we measure, and discrete data is data that we count. So we're not talking about, yes, no, holes, number of defectives, defects. We're talking about things that we can measure here, like my weight is an example. And all of these hypothesis tests on the right in bold are for normal distribution. So everything has to be stable. And some cases, like last time, we looked at the average temperature, which is the mean. So what we're looking for is we're comparing the mean of a sample compared to the mean of the last 100 years of temperatures in July. And then how many samples you can do at once. So all these things are going to give us some clues on which one of these hypothesis tests we're going to use. All right. And again, you can see that in column 2, the type of distribution is normal. The homework for after this class is for you guys to do exactly what I'm going to do right now. I'm going to take you through it on how to do a test for normality with data. So what I took was, it looks like I just took the first 7 months or so of my weight data back in 2006. So I don't have a ton here of data, right? I have, let's see how many pieces of data I have. You see down here on the bottom, I got 20 pieces of data. Is that a bell-shaped curve? Is the process stable? But I need to know that before I can start to apply any kind of hypothesis test to it. So here's how we do it. I put the steps right here, and I'm going to walk you through it right now. So you guys, then I'll erase it and I'll send you the math practice, and you can try it. All right. So first thing is rank use. So I have a column rank, one called index, one called z-score. So I'm going to do 3 things with my data. First, rank use is equals. Just type in rank, grab it, and then it's going to ask me for stuff. It's going to ask me for a number, and then a comma, and that's asking me for a reference. The reference is all of the data that I want to rank. And I got to kind of lock that in using dollar signs before and after each. And again, you guys will have the video, so you can kind of go step by step. And comma. And then according to the instruction, it says ascending order, right? So I'll grab ascending and double click. Single click, I mean, and I get 194 is ranked 8 out of these 20. Double click, and you'll see that every 194 is ranked 8th. Just to double check. Yep, we're good. So we just ranked them 1 through, looks like 19, because we have some duplicates in there. And then index is equals, and parentheses, the rank, minus 3/8, the formula, parentheses, divided by the rank, plus 1/4. That's the formula. It's right there on the steps. You can see it. Hit enter. Oh. Let me just double check. E equals C2 minus, I'm sorry, that's 3/8. And then,
You just got to put parens down around the
yep.
denominator.
Yep. Thank you. Saw it. Who's that?
Dave Terry. Dave Terry.
Thank you, David.
Welcome.
And I don't have to lock anything in there. And just double click all the way down. And then the z-score, I'm going to use equals norm m and probability, which is an index. And then I'm comparing this data to a perfect bell-shaped curve where the mean is going to be 0, so z. So the mean is going to be 0, just type in 0, and the standard deviation is 1. So I'm basically doing a comparison. I'm going to do a correlation between this set of data, these 20 pieces of data, and a perfect bell-shaped curve. And 1.43, double click. And you can see the correlation filled in because I had the formula already loaded up. But the idea there is, I'll just do it so it's the formula. We're gonna get into correlation next time, or when we get into the improved part. So equals Corel, and I'm gonna grab B and E. And the idea is that the closer to 1 I am, the closer we have a good positive correlation between this 20 pieces of weight that I took back in 2006 and a perfect bell-shaped curve. So it's highly correlated. Excuse me. And now I can graph it just by grabbing the weight and the z-score. And I can insert a chart. Looks good. And put a trend line on it. Where's the trend line? Anyway, that's the homework. I got a nice straight line here, correlation of 0.96. So I know that this is very close to a bell-shaped curve. So I know my data is normal. So I can use any of these tests, depending on what I'm trying to find out, which we're going to dig into some more. All right, that's the homework. Another type of test, you'll see single sample t-test. I hope it's not too small for you guys. Continuous data. My data is normal. The purpose is, again, the mean, the average of something. I have one sample, and the standard deviation is not known of the population, okay? And I'll explain that right now, what that means. Oh, I put the chart here. Never mind. Dirt. So what I want to show you was the single sample t-test. This is another example of a test I would use. This is, again, for small samples. Like I don't have a ton of samples. Remember that T, student T? It's so I don't have to go out and catch 10,000 whales in order to get a good number. So this test, the example I like is that a typical supermarket trip takes 22 minutes. And to test this, we selected 50 shoppers. The mean shopping time for those 50 shoppers was 25.36 minutes. Okay, so the typical trip takes 22 minutes. And, we took a sample. So I have one sample of 50 shoppers. And it was 25.36 minutes. And it has this with a standard deviation of 7.24 minutes. So, when I started recording the time for those 50 shoppers, some of them were 32 minutes, some of them were 18 minutes. But the average variation was 7.24 minutes. Now, you notice we don't know what the standard deviation is for all shoppers because we didn't. So that's unknown, right? So this is a perfect opportunity to use the single sample t-test. So using a 0.1 level of significance, which is another way of saying using a 90% confidence level, is there evidence that the average shopping time of these 50, 25.36 minutes, is different from the claimed value of 22 minutes? All right, so let's start there. The first thing we're going to do is select what kind of distribution we have. We know, I'm telling you ahead of time, that this is a normal distribution of the 50. So we're going to be able to use one of these. It's continuous data because it's something that we measure, right? We're measuring the time to shop. So it's continuous data, normal distribution. We're talking about the average of something, the mean of something, the mean shopping time. So we're not going to use these down on the bottom. We're not going to use chi-square, F-test, or Bartlett's. We know we're going to be using one of these up here. We don't know, again, we don't know the standard deviation for whatever came up with that 22 minutes. We don't know that. Like, in other words, a typical supermarket trip, whatever that was, we don't. So we have only really one standard deviation or average time away from the average, right? So the hypothesis test, is this a one or a two-tail test? First, let's start with that. Anybody?
Maybe a 1.
Okay, well, why would it be a 1?
No. Sorry, two.
Yeah, because I'm not asking if it takes longer or shorter, right? All I'm asking is it different?
Right.
Right? Different. If I say it's, is this significantly longer? So that'll be one tail. So that matters because my hypothesis test is going to be two positions. One is going to be the null hypothesis, which means that it's equal to 22 minutes. And the alternative is that it's not significantly, it is significantly different. So it's not equal to 22 minutes, right? And again, a significant value is 90%, want to be 90% sure. And the first thing we're going to find is what formula did we use to do this one-way f-test. And there's the formula, where it's called a t-test, a t-statistic, I'm sorry. So it's equal to x, which is the, fill them in, which is the 25.36 minutes, which is what I found for the 50 shoppers, minus the average for the population, which is 22 minutes, divided by the standard deviation, divided by the square root of the number of the size of the sample. Anyway, you come up with a test. And again, you may want to use this test during the final exam, when you do the final presentation, I mean. And when you do all that math, it comes out to a test statistic of 3.28 minutes. And I have to go into a t-table. And for a t-table, I'm looking at the degrees of freedom. And degrees of freedom, all it means is take the number of in the sample, which is 50, and minus 1. Degrees of freedom is 49. And in order to get, I got to go into a table. And my degree of freedom was, my confidence level was 90%, right? 90, sorry. Yep. 0.1. And I'm going to go to 49. Here's the column for 90% confidence level. And my degree of freedom are 49. So the closest I can get is 1.684. 1.676 is 50. So we'll use that. And that's going to be my goalpost right there. 1.7. That's how I got it out of the table though, guys. So there's my confidence level. And then degrees of freedom is nothing more than the size of my sample minus 1. So go all the way down to 49. So I had 50 in my sample, but I don't have 49 here. So I'm going to take the closest one. And because I'm using the 90% degree of freedom, confidence level, that's where I take the number from, 1.676 out of this column. If I was going to take it out of, if I wanted to be 99% sure, then I would have gone down in this column here, 99 column, and got that goalpost. So I set the goalpost up, 1.7, 1.7. My test statistic is 3.28 minutes. So can I reject the null hypothesis? Anybody but Dave Terry. Can I reject the null? Anyone? Give it a go. Dave?
Yeah.
Am I going to reject the null?
Yes.
Right? Because it's outside the rejection region, 3.28.
Yep.
So if it was in either rejection region, say it came out to 0.8, then I would reject the null also. So all it means is that shopping time is not as advertised. So that's the single sample t-test. And we're going to talk, another one that I think is worth showing is the ANOVA one-way f-test. This looks complicated, but it really isn't, because it's really just going to follow the same steps. And all ANOVA f-test is going to talk about is more than 2 samples. So in this case, we're looking at stress levels for people that work in column 1 here, from 4 p.m. to 12 a.m. We want to compare the average stress levels of 3 shifts. So second shift, third shift, and first shift. And these are arbitrarily measured. And there's a way, but we have to first, again, come up with a test statistic for that. In this case, the information we're going to need here is how many pieces of data we have in each of the shifts. We're going to need the total count. All 3 shifts combined, how many of those we have. We're going to need the average of each group. And I'm gonna send this to you in case you guys want to mess around with it a little bit. And then the grand mean is all the data, the mean of all of it for these three, the average of these three numbers. And then we have K, which is number of groups. So this is all the information we need to do in order to figure out if there is the null hypothesis here would be that mean number one is equal to the mean number two, which is equal to the mean number three, which means there's no difference from a stress level between the three shifts. And the alternative again is that there is a difference. And we want to do it to a 95% confidence level. So then we go ahead and do the math. And here you can see the formulas that we have to go. This is, guys, this is all longhand, and you don't have to go ahead and do that. And this is what I kind of did here. You can see I kind of went through and did the calculations based on these formulas in order to come up with all that. You don't need to do that because as you can see down here in our handy dandy data package, it automatically does it like we did for descriptive statistics, where it kind of tells you we're going to get into the F critical and the F test. It's an F test. So I have an F critical, which is from a table. And just by highlighting the data, this just pops out, which would be the second part of the homework. I'm going to just leave this blank, and I just like you to use, because they don't have to go through anymore with a calculator. And yeah, there's a table for the F test, for the ANOVA. And I think what I like you to take away from this is that, ANOVA is used when I'm, looking at three or more variables. And there's a heck of a lot of math. And here's the actual formulas. Once you get all this stuff done with your calculator, your fingers, your toes, there's the formulas. And all it's doing is coming up with a test statistic of 27.58. The magic of the add-in that we did a couple weeks ago, there's my F statistic. And there's a number that comes right out of the table, 3.28, which is right here. So again, I think that's, and I think I'm going to let you guys try to figure it out using the add-in. So part one of the homework, normality. So, just going through the math of doing that. And then two, real quick one is how to do a hypothesis test with a couple of pushes of your mouse. Any questions, guys? Thoughts? But again, there's the same steps here. If you think about it, right? One, I have a statement, then I have to do a null and alternative hypothesis. I have to determine the confidence level. I have to come up with a test statistic, which is up here on the right in the gray. And I'm going to take that number and compare it to a critical value, which I'm going to take out a table. And there's a table for every hypothesis test we have. All right. Any questions? And I think important part is just knowing what kind of data am I looking at? What test do I pick? Yeah. All right, let's get into PowerPoint. Hopefully it'll be it won't be, we're going to fly through it. Boy, it's dark in my office. Let me turn my light on. Got dark quick, December 11th. Let's see. Everybody's awake? Hope. All right, here we go. Yes. Thank you, Kim. At least I know Kim's awake. I know Dave's awake. All right. So last time we got into multivariate analysis, which is a really cool tool because it allows us to look at many different variables at once. I think I used the yogurt shop, size and location. It's kind of a neat graphical tool. We talked a little bit about classes of distribution. We're going to talk about some more today. And we talked about inferential statistics, which is and this is kind of where hypothesis testing comes in, where we're trying to infer, we're trying to make conclusions from a sample of a population. We can't go out and get the whole population. So we want to make sure we got the right number of samples. We want to make sure we get something that's representative of the population. so we can start to make conclusions and start doing some improvement work when it's all said and done. A good example might be I do a hypothesis test on my weight data and say, well, a null hypothesis might be Bill's weight Christmas week is the same as, is not significantly statistically different on average than the rest of the year. Well, let's say I came back and I was able to disprove that null hypothesis. Well, maybe I'd be making some improvements, like not eating so many shrimp or all the hors d'oeuvres that I love, and maybe not eat as much. But again, the whole purpose of this is, yeah, I got a lot of data. I don't want to jump to conclusions and just jump to solutions, make improvements willy-nilly. I want to make smart improvements. So that's what this whole analyze phase is about. Define the problem, measure it. And now that I've measured it, I want to analyze it so I make really good, smart improvements. And we just flew over hypothesis testing, practical versus statistical significance. We always talk about, is the weather on that date statistically significantly different, or it could be statistically significantly hotter or colder. Is my weight heavier or lighter? Same thing. But we're looking at statistical significance versus practical. And we talked about risk. I think that's really confusing. All the different ways you can talk about it. I just love confidence level, 90, 95, or 98. And I love rejection region. If that's how it makes it real simple for me. We talked about how to read tables. We had a little practice with that. And today, testing for normality, which I showed you how to do. And we're going to talk about hypothesis tests, a bunch of them with normal data, which is bell-shaped curve. We talk about tests of equal variance. When I'm looking at two samples from two populations, I want to know if the variation is the same in each. Now I have an example of that I'm going to show you. We'll talk about z-test, which we already did with my weight. We're going to talk about one sample t-test, which we just did. A two sample t-test is the same as a one sample t-test, except anybody want to guess what the difference is? Two samples instead of one. We're going to talk about one sample variance chi-square. I have an example of one of those, and one-way ANOVA. And then next week, we're going to do all the non-normal data. So same thing with non-normal data and also with discrete data, which is stuff that we count, like polls and stuff like yes, no, all that, ratings, that kind of thing. All right, so testing for normality, we could fly through this because it's our homework. Because it's one of the first questions, so I need to know which one I can use. Which test do I need to use? So I want to know if my data is normal. And it'll impact how we analyze and interpret it. It's not a given. And there's some physical limitations that restrict the ability of normality. An example would be if I was going to measure how fast or how far someone can throw a baseball, I can't get something to the left, right? I can't get something to the left of the bell-shaped curve there, right? So I can't, this can't be normal, right? Phone call duration cannot have a negative time. So there's certain times that I'm not going to have normal data. And normality test, I showed you the formula, but basically we're comparing the p-value versus the alpha level, and we're comparing our data to a perfect bell-shaped curve. And that's what we did with the little exercise. And let's go through some hypothesis testing with normal data. Here's the steps. I don't think I need to go through them. We've already gone through them 3 times today, right? And here's the chart. We've already talked about the z-test, the one sample t-test. And again, it starts with the data type, what kind of distribution I have. I might have to do the normality test to see if my data is normal. And the purpose. And how many samples. It's actually going to depend on which test I use. And do I know the standard deviation or do I not know the standard deviation? But it kind of zeroes you in on what's the best hypothesis test to use. So let's start with tests of equal variance. And again, to check whether the variances of two populations. So variance is nothing more than the standard deviation squared. You remember from math practice, I think the weight, the standard deviation of all those 800 pieces of weight that I gave you was 4 pounds, and the variance was 16 pounds, somewhere around there. And to check the variances, the null hypothesis is that the standard deviation squared, or the variance, of population 1 is equal to the standard deviation squared of population 2. And simply enough, the alternative would be that it's not equal. And you can use it as a prerequisite for other statistical tests. One example, F test is one example. And again, these are tests of variance, not mean, right? Not average. We were looking at mean temperature. We were looking at mean shopping time. We were looking at mean weight. In this case, we're looking at a difference between two populations, variance or standard deviation. If I only have the standard deviation, I square it, or I might be given in some problems, which I think I'm going to show you one of them, an example of one, where they give us the variation between two populations. The F test is extremely sensitive to non-normality, and that's when you use Brown-Forsyth. On the left here, here's the criteria for using the F test. So it's got to be continuance. We're not looking at mean, we're looking at variance. Normality is not required, but it's very sensitive here, and we're going to always have two samples. And there's a test statistic for it right there. Like again, first thing we do is there's a test statistic goes with every single one of these hypothesis tests. And we're going to compare it to a critical value, which we're going to take out of a F table. And in this case, we're looking at the standard deviation squared of the bigger one, whichever the bigger one is, the bigger variance of the two populations. I think the one, let me see the example. I might just jump to that. I don't, maybe not. I think I did it for chi-square. But again, so the bigger variation goes on top. Let me slow down. The bigger standard deviation squared goes on top. So in other words, the population of the more deviation goes on top. And I'm just trying to figure out, is there more variation in population 1 or population 2? That's all. Is there more variation in the height of boys in the 3rd grade versus girls in the 3rd grade? Right. I wouldn't go out and get and measure all that, right? I have to get a sample, but all I want to know is, so I want to know, all right, take my sample, figure out what the standard deviation is, and then and go from there. And once I have the F calc, I'm going to put it into a compare the number to a table and see if I can reject it. And there's other tests for equal variance. I'm just going to kind of just brush on those. Bartlett's test is to test if samples from populations with equal variances. So we know they have equal variances. Levine's is inferential statistic to assess equality of variances for a variable calculated for 2 or more groups. So it might be breeds of dog, maybe the weights of breeds of dog, 4 or 5 of them, maybe. And then Brown-Forsyth is for equality of non-normal group variances. But we're not going to, really, I've never used these myself. So, I mean, just kind of for information only for you, not on the exam. And then unequal variances are usually a result of differences in the shape of the distributions, like extreme tails, a lot of outliers, multiple modes, where the same data point shows up over and over. And it should be explored through data demographics. Anyway, let's get through that. Z-tests. Again, this is something we've seen a couple weeks ago, I think. Simplest normal distribution, where the mean is equal to 0 and the variance is equal to 1. Right? So the 0 is that, and a bell-shaped curve is where the mean is, and the variance is equal to 1. So we go 1, 2, 3 on one side, -1, -2, -3 on the other. And that's what when we did our normality test, that's what we used. It's how many standard deviations is above or below the mean, and we use lookup tables to find the population. So a 1 or 2 sample z-test, continuous data, we're looking at average, it's normally distributed, 1 or 2 samples, small sample size, standard deviation is known. And again, there's the null hypothesis, and we have a test statistic, and we're going to compare that to a table and see if we can reject the null hypothesis. And some decision rules, identify the Z critical from the Z table. And again, over and over, right? With the same process. A 1 sample t-test, as we just did. So we're looking at the mean of a single sample against the target. So we're looking at the mean of a single sample of 50 shoppers and how long it took. It could be one piece of equipment to another. It could be supplier A's quality to supplier B's quality. It could be performance of products before and after a given process. It's also known as student T, which was, remember, we don't need to have more than 30 samples to do this. And it's a hypothesis test to study whether there's statistically significant difference between a population mean. And the population mean was, what, 22 minutes, I think it was, right, for shopping, and a specified value, which was the average of those 50 shoppers, which came in at 26 minutes. And there's the null and alternative hypothesis. And there's the formula that we used on that shopping one. And the 2 sample t-test is comparing 2 populations. Maybe it might be before and after a treatment, but using the same population twice, before and after a treatment, for example. Variants are unknown but assumed equal, or variances are unknown but assumed unequal. It's a hypothesis test to study if there's statistically significant difference between the means of 2 populations, where mean 1 is the mean of one population and mean 2 is the mean of the other population of interest. The focus is unknown, unequal variances. But obviously more than 1 sample. So we just looked at 1 sample, right, in the supermarket. Let's say I want to look at 2 or 3. I'd use a 2 sample. And there's the paired one, the paired t-test. You want to know if there's a statistically significant difference between the means of the same sample before and after. And sales before and after training, for example, measuring somebody's sales before training, and then we train all our salespeople, and we train them again, and we look at their sales afterward. That might be a place where I'd use this 2 sample paired t-test. And 1 sample variance chi-squared. It's kind of it's a 1 sample goodness of fit test. Example I might use that might be, I have seasonal allergies. Does being born during a specific season influence a person's to develop allergies, for example? Is there a correlation between gender and reading a newspaper? Things like that. It's again, their criteria is continuous data. We're looking at variance, so we're looking at difference between 2 populations, normally distributed in 1 sample. And it's a statistical hypothesis test where the test statistic follows a chi-square distribution. So it's not a bell-shaped curve, but it's fat one way or the other, right? I think I'm going to show you an example using test scores. Same idea though, except I could have, the variation of 1, 2, all the way up to 50 if I want. And the alternative hypothesis, at least 1 is different. And there's a formula for it. So all I'm doing is getting a test statistic there. Here's the example I'm using. The standard deviation of exam scores of a local college is 8.6. A professor believes this value is less. So we're looking again at standard deviation, right? How much difference is there from the average? He samples 20 exam scores and finds the standard deviation 6.9. Does this sample provide enough evidence to suggest that the true standard deviation is less than 8.6? All right. So the null hypothesis is that 8.6 squared, the variance is 8.6 squared. So the null hypothesis is that the standard deviation squared is equal to 8.6 squared, and the alternative is that it is less than. So when he says less than, right away we're thinking it's a one-tailed test. So we're looking at, and this is a perfect example of what a chi-square distribution looks like. It's not a perfect bell-shaped curve. It's a lot fatter down one end. And I go into the table and I come up with a critical value of 10.117 based on a 95% alpha confidence level. And I come up with, so that's where the 10.117 comes. I'm only looking at, the left side of the graph. And I could see where the rejection region is, and my calculated number using the formula is 12.23. So I know that it's in the bell here. It's not a bell, but it's it's not in the rejection region. So I cannot reject the null hypothesis. So it's all the same theme, guys. It just depends on what you want to know, what you have for data. And just the only way to learn is just try it. And I'm hoping, whatever data set you pick for the final presentation, I'll put you in teams of 3 or 4 people working together. You can use my weight. I think I was talking to Matthew Schwartz or Sebastian at Atlas about using some scrap data, wherever you guys out in Colorado. The presentation is going to be people from different companies. Like I like to mix it up a little bit. Where Dan, you might be with somebody from Colorado. Yeah, that's chi-square. And again, just a reminder, these are the distributions that we look at, that we use mostly. It's basically a pattern of data. We're looking for a pattern of data, and with normal, student T, chi-square being the most common. Binomial is yes, no. So I'm using that for discrete data. Pass, no, go, no go, stuff like that. And then the last test I think we're going to talk about today is the one-way ANOVA, which is what we just did with the stress levels, different shifts. So it's continuous data. We're looking at the average. We're looking at something that's normally distributed. We're looking at more than 2 means, averages. We're looking at equal variances, but it compares the means of different groups by analyzing the variances between them. And it's a generalized form of the 2-sample t-test. And it has a null and alternative hypothesis. And based on the data, the means of the 3 populations might look different because of 2 variation sources. There's variation between groups and there's variation within groups. So we looked at variation within the shift and also across the shifts, if you remember. So this is a case for ANOVA when you have situations like that you want to look at. And we care most about the variation between groups since we're interested in whether groups are statistically different from each other. Is the stress level between the shifts different? But I'm just trying to give you a sense of when I would ever use ANOVA, right? Let's say students from different colleges take the same exam and you want to see if one college outperforms the other, or a group of psychiatric patients are trying 3 different therapies, counseling, medication, and biofeedback. You want to see if one therapy is better than the other. Statistically better, right? Statistically significantly better. Yeah. And it's like, for example, supplier A, supplier B. So I think you might get the idea there with ANOVA. And there's that beautiful formula that I showed you over on math practice, where I'm looking at the sum of squares of everything, total variation, variation between groups, variation within groups. And the beautiful part of it is using the add-in in Excel, just by highlighting data, it tells us our F statistic and it tells us what comes out of a table. And I might go back into that. I think I'm going to go back in Excel and just show you where it is. And I'd like to just mess around with it. And when it's all said and done, it comes down to, can we reject the null hypothesis? ANOVA is a modeling procedure, and to make the conclusions reliable, we need to perform residuals analysis, which we're going to cover in the improve phase. And residuals have a mean of 0 or normally distributed. We're going to cover all that next time around in the next phase. And if the variances are not all equal, use other hypothesis testing methods other than one-way ANOVA. All right. And I think I'm going to stop there. We're going to just tackle the test for non-normal data, which are these. We're going to just pick a few of them just to give you a taste of it. And stop sharing. And let me go back into math practice for a sec. Right, move this out of the way. And I just wanted to show you in data again. This is a review, data analysis pack, and you'll see down here. And so we're doing an F test, right? 2 sample for variances, one way. I think what I might do is do a quick video and do that for you. And how to, because basically all I'm gonna ask you to do is take that set of data, the stress data, and use this tool to give us the answer. Try it without me going through it with you. And just pop me a note if you want me to send you how, okay? And it is 4:17. I was gonna try to sneak in another, like get the whole thing done, like all of this analyze phase. But I don't know. I think it's too much. Anyway, thanks for showing up, people. I'll send you off the math practice, the video. Homework will be due next week. And we got to talk about how we want to handle it over the holidays, with Christmas and New Year's both being on Mondays. I don't think you guys want to show up Christmas. Nor do I. My grandkids will be not too happy with Papa. Have a great afternoon, people.
Have a great one, guys. Thank you,
Thanks
Bill.
for
Thanks
hanging
for
in,
Bill.
everyone.
Thank you.